Let's start our lessons today. So we continue with spectrum and something additional theorems which can help us to find the spectrum. I begin with definition. Weyl sequence. What it is mean? Weyl sequence. We have X Banach space. We have bounded operator in this space, and we say that for complex number lambda, for complex lambda, they exist Weyl sequence xn if the norm of any element is 1 from this sequence and the result of operator on this sequence tends to the 0. So, for example, if we take a stable sequence from eigenvector, what you have, and lambda is eigenvalue, the stable sequence of that lambda is eigenvalue and xn equals n eigenvector, what we have? It is 0. It is 0. For example, for stable sequence of eigenvectors, it is 0. And you can normalize eigenvector on unit, on 1, yes? But it is possible that it is not 0, but it tends to the 0. Okay. So it is almost eigenvector, yeah? And so theorem, if for lambda complex exists Weyl sequence xn, then lambda belongs to the spectrum of operator. To the spectrum of operator. For some class of operator, it is criteria. For example, for self-adjoint operator. For self-adjoint operator and for normal operators, lambda lies in spectrum if and only if exists Weyl sequence. Moreover, if you a priori know that the operator has no residual spectrum, if you know a priori that residual spectrum is empty, then it is a criteria. Because you need to work only with a continuous spectrum and point spectrum. For point spectrum, it is obvious, yes, by this example. Proof. By contradiction. Let lambda is from a resolvent set. Let lambda is from the resolvent set. Then you have inverse operator, yes? They exist. Which is bounded. Let us denote Yn is the result of our operator on the xn. Xn is Weyl sequence. What we know about Yn by definition of Weyl sequence? It tends to the 0, yes? So Yn tends to the 0. Let's take the inverse operator, let's take the resolvent and consider what we obtain in this action. What is this result? by definition of this? It is xn. It is just xn. It is don't tend to the 0 because by definition the Weyl sequence is normalized sequence. So contradiction with what? Bounded operator is continuous operator. So this is tend to the 0 and the result is not tend to the 0. It is contradiction for continuity of operator. It's contradiction. It is contradiction. Okay? So how we can use it? We can use it in following theorem, which I formulate on the previous seminar. Yes, I formulated about the spectrum of operator of multiplication and function. So theorem as illustration of using of this theorem for Weyl sequence. Yes, not H. A phi acts in L2AB to L2AB in Hilbert space, where phi is function from L infinity AB. Operator of multiplication on function. Phi of x multiplied to f of x. Then spectrum of this operator is essential values of function phi, which I denote as essential E of phi is just such lambda that for any positive epsilon, the measure of such x that phi of x minus lambda less than epsilon is positive. It is just a definition of this set. All this set is just a spectrum of operator. So they are the same. And what about classification? This operator is normal. We know, yes? This operator is normal. That implies that residual spectrum is empty. Residual spectrum is empty. So we need to discuss when we have a point spectrum and when we have a continuous spectrum. If exists a set, measurable set, just omega such that measure of omega positive is positive and phi be reduced on this omega is constant. So is function is constant on the set with a positive measure, then lambda is a point spectrum. And other points from essential values are continuous spectrum. A continuous spectrum. But in applications, usually we have a function phi is continuous, of course. For continuous function on the interval, all essential values are just values of function. by definition of continuity. Because this set is integral for continuous function. Yep. Is it clear? Okay. Question?
This can be seen like a generalization or similar to the case of one home problem that is L2, the product of alpha, the dot product of alpha with an element of L2. We need to find the spectrum of this.
Yes.
And in one case, I found that the eigenvalues are when almost we have an infinite number of elements, the same element.
Yes.
It's similar like this. We have in a set of measure, we have the same.
You want to compare this operator with operator on multiplication on the sequence in L2 small, yes?
Yes. There is, I think, an analogy between these conditions.
But no, in this situation, if you want to consider this operator, A alpha x equals alpha 1 x1 alpha n xn and so on, point spectrum just all these elements. Point spectrum is just the sequence alpha k.
Alpha k?
Yes.
Okay, yes. Okay.
So your function can be equal to, here function, yes, function on the natural numbers is a sequence. So it must be equal to alpha n on the one coincide with lambda, just at least at one coordinate. But okay, this coordinate in this situation have measure 1. We have a discrete measure. Yes. But if you write, if I write L2 without measure, it just means that we use classic Lebesgue measure, the length of interval. But of course, if you consider L2 on some set omega, if you take omega equals to natural numbers, if you take sigma algebra of measurable set as all possible, and if you defined measure for such for natural number equals to 1, and then continue it as sigma additive measure, then immediately it's changed to L2, and integral change to the sum, of course. But it's here when we write AB, so it is classical measure, Lebesgue measure, so it's length of interval. Okay, so let's prove this theorem. And I repeat again that for many applications in practice, function phi is continuous, but you can multiplicate it on not continuous function. For example, on signum. We have this example, yes, that 0 for signum is not essential value. -1 and 1 is essential value. And 0 is not essential value. Because preimage of a small neighborhood of 0 is have measure 0. In one direction, we use this theorem. We construct a Weyl sequence. So proof. First, let lambda belongs to the essential value of function phi. That by definition, for any natural n, the measure of such points x for which we have this inequality is positive, yes? I change epsilon continuous parameter on discrete parameter 1 over n for convenience. It's just the same, yes? So it's like epsilon. Let's denote this set Mn. It is set, yes? And then define It is, of course, measurable set, because function phi is from L infinity, it's measurable functions. And define function fn as characteristic function of set mn divided on square root of the measure mn. So here omega, I remind, is 1 if x from omega and 0 in another case. Yeah? It is indicator of characteristic function. Okay, yes? What you can say about the norm of this function in L2? 1. And now let's calculate this. It equals the integral on the set Mn only, yes? Phi minus lambda square. Fn here is 1 by definition of characteristic function, divided on the measure of Mn. And integral, Lebesgue integral dmu. It is the action of operator. Yeah? It is the action of operator. Function Fn on this set is 1. So we needn't write it. And I write the square of them. So here square and the square in the denominator. What is estimation of this enumerator? By definition of the essential value, lambda is essential value, it is less than 1 over n square. The numerator, and then you integrate the inverse to the measure by the set with the same measure. So it is 1. So you have this estimation, it tends to the 0. So Fn is a Weyl sequence. So lambda is from the spectrum by our theorem. And now proof inverse. Second, let lambda is not from S. Let's show that lambda is from resolvent set of operator. So combine these two steps, we understand that lambda in the spectrum, if and only if it is essential value, yes? And if we want to show that it is from resolvent, we must construct the resolvent operator. By definition, what it means with this? So you must write the contradiction to be lambda, that lambda is from essential values, yes? So there exists lambda positive, epsilon positive. Then that measure of such x that phi of x minus lambda is less than epsilon, this measure is 0. Yes? Let's define this set again. M epsilon. M epsilon. And what means, what does it mean, what we need to do to construct the resolvent? It is just the same as to solve this equation. Yes? To construct the inverse operator, the resolvent, is equivalent to solve equation. This. Yes? If we solve equation, if we for function g is known, we must obtain function f. It is just the same. You construct the inverse operator. If you can say, if you can reconstruct f by g, it is the same to reconstruct the resolvent operator. So this equation I rewrite in this form. And to find f, it is sufficient to divide on the first term, yes? If you want to find f, it is sufficient to divide on the first factor. But dividing is a bad operation because this factor can be small. And if you divide on this, then function f can be large. And it can be not lie in L2. It is not sufficient to construct f. You must construct function f from L2. So function g is from L2, is given. It is from L2. Our operator acts in L2, is given. So function f must be in L2. Let's write division, but we just decide where, on what set we can divide and on what set we cannot divide. If this value of phi minus lambda is not small, you can divide. Let's look on the definition of side m epsilon. Fx minus lambda less than epsilon. Less. So if x do not belongs to m epsilon, so the difference phi of x minus lambda is a part of 0. It is greater than 1 over epsilon. So you can divide on this set. Or if x is from m epsilon, how you can define function f? What is the space L2? It is not a space of functions. It is space of class of equivalent functions. You can change function on any set of measure of 0 measure. It is the same element from L2, the same element. And this set has measure 0. So you can define function f as you want. For simplicity, yes. For simplicity, 0. For simplicity, 0. And what we need to do? We need to do that this operator, it is just resolvent L lambda A. I remind that it's the same, this notation is similar for this operator. This is the same. So we need to check that this operator is bounded. So question, if this operator is bounded. Okay. Let's check it. And I again write the square of the norm. Because I don't want to write square roots. It is by definition g of x square phi x minus lambda square d nu ab without m epsilon, yes? Integration on interval ab without m epsilon, because on m epsilon we have 0. But on this set, of function f of x is less than epsilon, yes? Greater than epsilon on this set. By definition of m epsilon. So we can write estimation and this is less than 1 over epsilon square integration of all over AB. So we immediately obtain that and here epsilon is not tends to the 0, it is just one fixed number. It is a characteristic of number lambda. It is characteristic of lambda when lambda is not from the essential values of function phi. Yeah? So it is bounded. So we construct the resultant, so lambda is from the resultant set of operator. And what we need to show is just only discuss the classification, yes? So I can again repeat that this operator is normal, so the residual spectrum is empty. Okay? So we just want to decide when lambda is from point spectrum and when it is from continuous. So we have only two parts of spectrum here. So classification of spectrum. It is easy. Because it is easy if you understand what happens with the function in L2 when it is not 0. Element of L2 is not 0. It must be not 0 on the measure with positive, on the set of with positive measure. So when lambda belongs to the point spectrum, means that exists f from L2, AB, and f is not 0 in L2. It means exists omega, measurable set with positive measure, and f is not 0 everywhere for any x in omega. And now consider this eigenvalue problem. It means that phi of x minus lambda f of x must be 0 in L2. This product must be 0 in L2. And we know that it is not 0 on omega. So what we can conclude for first factor? It is not 0 on omega. So this must be 0 on omega. So function phi is constant on the set with positive measure. No? So it is necessary and sufficient condition for existence of point spectrum. Yeah? So residual spectrum again empty. So another points are from continuous spectrum. Yeah? So another points from essential values are in sigma c. That's all. That's all about operator of multiplication on bounded function in L2 on the interval. Be attentive, some of you get the second personal task. They may be operator on the L2R. So you must consider some modification. Maybe. because on the infinite domains, for example, on the real axis, for continuous function, it is possible that there exists essential value, which is not a value. On the interval, each essential value for continuous function is a value of function. And inverse is right. Any value is essential value. It is on the interval. But on the real axis, it can be not true. For example, consider function phi of x equals 1 x squared plus 1. And multiplication of this function in L2 on this. Try to understand what is the spectrum. 0 is not a value of this function, but it is essential value. It is essential value. So, and now simplification of this theorem. What happens if we consider the same operator in another space, in the space of continuous function? The answer looks like SNL2 with some little modification, but investigations is just more simple. So theorem, next theorem, phi is continuous function. Operator A phi is from continuous function to continuous function. It is just, again, multiplication. What is the spectrum in this situation? Spectrum of operator A phi is just the values of function phi. So such lambda that exists x from AB such that lambda equals phi of x. We can define that as image or range of function phi. Yeah? Just a value. And classification, lambda is from point spectrum if and only if exists interval alpha beta from AB such the function phi is constant. Is a constant. Not positive. It is of course positive measure, but it is just an interval. For example, you can consider Cantor type set with positive measure. It has no interval inside this set, but it has positive measure. It in comparison with the previous theorem. But here, function phi must be 2. So in previous theorem, function phi can be constant on measure on the set with positive measure. But this set can contain no interval. And here must be constant just on interval. Other points, from range of phi belongs to residual spectrum. Residual spectrum. So multiplication in L2 is point spectrum or continuous spectrum. And multiplication of function in continuous function is a point spectrum or residual spectrum. You see the difference, yeah? So proof of this theorem. First, if lambda belongs to the value of phi, then consider this function f it is from range of operator A phi, yes? And by definition, what it means? It means there exists point x lambda from AB such that lambda equals to the value of function phi in this point, yes? It's just a definition of values of function. What you can say about function g at this point? This is definition of function g. So calculate 0. So you see that the range of operator A phi is not all continuous function. So immediately it is in spectrum. Operator at least is not surjective. Second, inverse. Let not from the range of phi. What we know about the set of values of function phi? It is image of the closed set. So it is closed. It is closed. It's closed. And if it is closed, then the distance from lambda to the range is positive. Equals d is positive. And distance is, this is equals to the minimum range of phi. Phi x, yx belongs to AB. So again, try to construct a resolvent and check that this resolvent is bounded operator. So let's construct resolvent. Again, to construct resolvent is the same to solve the equation. So we need to solve the equation. Right side function g is given. We must find function f. The formula dividing, what we obtain? Formula. We obtain again operator of multiplication of the function. Yes, it is again an operator of multiplication of function, but inverse function. Not inverse, but 1 over this function, phi x minus lambda. What we know about the norm of operator of multiplication of function? We calculated. The norm of operator of multiplication on function. It is maximum of this function on interval or AB. So the norm of resolvent, it is just maximum on AB of this function. Maximum here. But denominator is constant, so when this ratio has maximum, it is just when we put into denominator minimum. But seeing this minimum is just a distance between lambda and the range of phi, it is positive. So it is equal 1 over d is less than infinity, so it is bounded. So our resolvent is bounded. So lambda is not from spectrum, lambda is from resolvent set. So we obtain that spectrum if and only if lambda lies in the values of function phi. Yeah. So just about classification. What we can say about classification? First, when lambda lies in point spectrum, again must be eigenfunction. Yes. So exist function f continuous, f not 0, and a phi acts on f equals lambda f. This is equation equivalent to what equation? For this equation, what means the function f is not 0 in class of continuous function? This means there exists point x0 in AB such that f at this point is not 0. But it is a continuous function. It is continuous function. So exists interval alpha beta, exists open interval alpha beta, that function f is not 0 on whole interval. So look on this equation. This is not 0 on interval alpha beta. So what conclusion we can make for first factor in this product? So we immediately obtain that phi x minus lambda 0 on alpha beta. So your function phi must be constant on the whole interval. Only in this situation we obtain point spectrum. And why are the points from the residual spectrum? Good. We have necessary part on the blackboard. If function lies from the range, other points. So second, other points from values function phi. So we know that lambda equals to function at some point x lambda, yes? Exists x lambda such that lambda equals to the value at this point. So if G lies in the range of operator a phi minus lambda e I, then G of x equals phi x minus lambda fx for some f, and G of x lambda equals to 0. We write it 5 minutes ago, but we need to repeat it. And now consider closure of this range. Closure is in the norm of CAB. It is uniform norm. Is uniform convergence preserves values at points? Yes, it is. The uniform convergence preserves the values at points. So if function h lies in the closure of operator, in the closure of the range of operator, and all points in the range has this property. So if you consider closure, then again 0. So the closure of the range is not all space. By definition, it is a residual spectrum. By definition, it is a residual spectrum. So that's all for this two class of operators. Very useful, very important class of operator of multiplication on function. So, for example, you know the spectrum. You can we consider just only bounded operators, but many things can be transformed to the unbounded operators. So operator in quantum mechanics, the operator of coordinate, is just a multiplication on the variable x. What is the spectrum of this operator? If you consider one-dimensional situation, L to R. Whole real axis here. It is self-adjoint operator, so spectrum is real too, as in bounded situation. But spectrum is unbounded because operator is unbounded. It is on property of compact and self-adjoint operator. Maybe you remember that when we consider the Gram-Schmidt procedure, I said that the humanity knows two basic ways to construct orthogonal bases in Hilbert space. First way, it take a linear independent system, which is closed, and by Gram-Schmidt procedure, it is the same Schmidt. The same Schmidt. With Gram-Schmidt procedure, you construct closed system but orthogonal. And by theorem, closed and orthogonal system is equivalent to B basis. Yes? Or you take complete linear dependent system and again make a Gram-Schmidt procedure and make it orthogonal. So again, it is basis. The second way, from theorem Hilbert-Schmidt. From theorem Hilbert-Schmidt. But it is not just formulation theorem because it is a large theme. So some auxiliary lemmas. First definition. Let's A is bounded in Hilbert space. H is Hilbert. Subspace H0 lies in H is invariant for A if for any x from H0 AX lies in H0. You take vector from subspace and the result lies again in the subspace. So lemma 1, if H0 is invariant for A, then the orthogonal complement is invariant for what operator? Adjoint. For adjoint. And the immediately corollary for self-adjoint operators, what? The complement, orthogonal complement is an invariant for operator A too. If A is self-adjoint. For arbitrary situation, it is the orthogonal complement is invariant for adjoint operator. And if operator self-adjoint, you immediately obtain two invariant subspaces. So proof of this lemma let X is from H0, Y from H0 orthogonal. We must prove that adjoint operator acting on Y lies in a orthogonal complement. Yes? Let's check this scalar product for any x from H0 and y from H0 orthogonal. By definition of adjoint operator, We know this equality. This is from H0 because it is invariant. And this is from H0 orthogonal. So it is 0. That's all. So AY star lies in H0 orthogonal. Yes? Good. So again, corollary, if A equals A star is invariant for A. So simple corollary is invariant for A. Okay? Just lemma 2. But before lemma 2, I want to remind. We have for self-adjoint operator, what we have? What gives us the supremum of quadratic form on unit sphere? Norm. We know what is norm. If exists vector with the unit norm such that x0 equal to norm. So it is attained on some vector. Yeah? So this number attained. Then this vector is eigenvector. And obvious in this situation, lambda can be plus norm or minus norm. Is it obvious? Because here absolute value. If this equals to absolute value of lambda equals to norm, so it is, can be just norm or minus norm. How we prove it? Assume that we work at least space with dimension not less than 2. In one-dimensional situation, linear operators is just operator of multiplication on numbers. Yes, it is not interesting. So assume that our dimension is not less than 2. So we have additional dimension for x0. So let's take z from H such that z norm is 1 and z orthogonal to x0. And now let's consider vector which depends on t as x0 cosine t plus z sine t. Let's consider such vector, linear combination. It's a circle in the two-dimensional, in plane which generates by vectors x0 and z. Yes? It's just a circle. Of course, by Pythagorean theorem, the norm of this vector is 1. Then, so it lies here. It lies here from the unit sphere. So we can consider the quadratic form for this operator, or for this vector, and consider function f of t, which equals the quadratic form on this vector x of t. And let's consider different values of t. what you can say about value of this function at 0? Yes? It is maximum or minimum of this function because the absolute value is supremum. On vector x0 we have an extremum of this function, so supremum. So without absolute values it is can be maximum or can be minimum. It is extremum. Extremum point. So what we can say about the derivative at this point? 0. So the must be 0. Let's calculate the function and derivative. So f of t equals I write it, but I take away brackets shortly. I think you understand it. So ax0 on x0 we obtain cosine square t ax0 z x0. Then we have factor cosine t sine t. It is when this ax0 multiplicates on this z or this x0 multiplicates on this z. And operator is self-adjoint, so it is can be written as Is it clear? Or I need to write more in more details? Okay. And plus sine quad t on quadratic form for vector z. Yes? This a z, z. So z, sine square is outside. And this can be written as sine 2t. So let's shortly calculate the value of derivative at 0. The derivative of cosine, it is 2 cosine minus sine. Yes? And sine at 0 is 0. Okay? The derivative of sine square is 2 sine cosine. And again, sine at 0, 0. But derivative of sine, 2t, it is cosine of 2t. No, 2 cosine, 2 cosine. And cosine at 0 is 1. So it is just equal to a real part of this semi-squilinear form. And then change z on iz, imaginary unit. Change. What happens with the real part? It is minus imaginary, yes, because I take it minus iz, so it is real ax0 iz equals to minus imaginary part ax0 z, yes, or plus. Sign doesn't matter because it is equal to 0, and this vector iz is of course again orthogonal to x, x0, and have a unit norm, of course. So it is changing this, we obtain, and this is 0. Real part equals to 0, imaginary part equals to 0. So we obtain that x0 equals to 0. So AX0 belongs to the orthogonal complement to Z. But Z was orthogonal to X0. So AX0 lies in the second orthogonal complement to X0. And we know happens, what gives us the second orthogonal complement. It is not the same, because I take one point and I can consider the second orthogonal complement to any arbitrary set. But orthogonal complement is always linear subspace which is closed. So it is equal to linear span of X0. It is linear span of X0. So we immediately obtain, and how looks like linear span of X0? It is X0 multiplied on arbitrary number lambda. So AX0 equals to lambda X0. So it is an eigenvector. So it's just like eigenvector. Okay. And this is obvious because quadratic form equals to lambda, yes? A x0 x0 equals lambda x0 x0. It is like lambda because x0 have a unit norm. So absolute value of lambda equals to the norm of operator A. So it is obvious. Lambda can be plus or minus norm. Okay. So we have two lemmas on the property of self-adjoint operator. But Hilbert-Schmidt theorem is on property of compact self-adjoint operator. So some properties of compact operator. Lemma 3. Let A is a compact operator in H. And let the sequence xn weakly converge to X. How you can say about in terms of continuous functions. Quadratic form of compact operator is weakly continuous function in convergence sense. It's not in epsilon delta terms, but in convergence sense, it is weakly continuous function. It is weakly converged, then we have usual converging of functions. Number valued functions, it's numbers. So quadratic form of compact operators is weakly continuous function. You can reformulate this lemma in this form. Quadratic form of compact operator is weakly continuous function. So let's prove. It's not difficult. Let's check it. Let's consider the difference of these two quadratic forms. Let's do simple trick, add something and subtract something. Minus AXXN plus AXXN minus AXX. And let's combine these with this and this combined with this by linearity of scalar product. How we can do it? Here, common element xn, so it is equal axn minus ax xn. And I combined it and use the triangle inequality with absolute value. And here we have this and this, so x ax multiplied in scalar product by xn minus x. What you can say about each term? So each term tends to the zero. Let's explain it. Why it? First, by Cauchy-Bunyakovsky, it is less than what we can say about the norm of xn. We know that xn weakly converges to x. So this sequence is weakly bounded. Any converging sequence is bounded. Weakly converging is weakly bounded. And we know that weakly bounded sets are bounded. So xn tends weakly to x, so xn is weakly bounded. So by Banach-Stengauss theorem, xn is bounded. So this is less than some number c, common for any n. What you can say about this factor, this norm? What compact operators do with weakly converging sequences? Make it converging in norm. Yes? So by property of compact operators, it tends to the zero. Because compact operators change weakly converging sequences to the sequences which converge in norm. So this we obtain that this is tends to the zero. Yes? What about this term? xn weakly converges to x. It means for any functionals. But in Hilbert space, all functionals are scalar product with some fixed element. Here some fixed element, ax. This is written functional which arises by element ax acting on an x minus x. So it is changed to the zero, go to the zero by weakly converging. By definition of this notation is clear. It's a function which generates by element ax. It is a continuous functional in Hilbert space. And what I need additional theorem, but it is geometrical theorem. I think I can prove it, but it is very long and technique proof. Theorem unit ball in Hilbert space is weakly compact. More. What it means? It means the following. For any sequence xn which lies in ball, you can choose weakly converging subsequence. Which converts to some element x.
This slide is weakly pre-compact.
Yes. No, just weakly compact. Because compact in metric space from any for any sequence you can find a converging subsequence.
Yes.
And weakly compact for any sequence you can choose weakly converging subsequence. Just let's without proof. Just if we need to, I can prove it. Because it's some geometrical fact. I can give only idea how you can prove it. The idea the same. Idea. On unit ball, the weak convergence coincide with coordinates converging. What is mean coordinate convergence? I just define it. On unit ball, xn tends to x and norm of xn less than 1 is equivalent that xn ek goes to x ek for any orthonormal basis. I consider only separable set, but the theorem is valid for not separable set. But you can easily prove it in separable set by this. On the unit ball, is it clear that from this you immediately obtain this? Because what means weak convergence? It means that for any functional, for any f from H0, yes? But how you can describe all functionals? All functional Hilbert space are scalar products. That you can write it as for any y, x and y go to xy. If for any y, so just for ek, for basis vectors 2. So in this situation, you do not need just this property even. But if you want to prove inverse, then you need the boundness of elements xn. Because in this situation, as xn weakly converges to x, it is necessarily bounded. Because it is weakly converged, so it is weakly bounded, so it is bounded in norm. But inverse, if you have this, then you decompose y in basis element, estimate the tail of representation of y by epsilon, the end of the series. And the first series, for first series, you have a coordinate convergence. For finite sum, you have coordinate convergence. So the tail of norm of y you estimate by epsilon, and then you can find such a sign that it first coordinates in sum less than epsilon. So we immediately obtain the convergence in weak sense for any y. It's idea. So, and then interesting analogy. What happens, what we know about continuous functions on compact? A lot of different properties. But one of important, any continuous function on compact attains its maximum and minimum. What you can say about weakly continuous functions on weakly compact set? Understand question? Yes? We have continuous function on compact set attains maximum. And we prove lemma 3 quadratic form of compact operators is weakly continuous function. And unit ball is weakly compact set in sequentially sense. And we have a full analogy. The weakly continuous functions attains maximum and minimum on weakly compact sets. We can prove it. It's not difficult. So, but it is, I think, this is an interesting fact. So, theorem. In metric space, I think it is in metric space, maybe. Yeah. Let's f capital is a weakly continuous function on weakly compact set. What it means? It means if xn, oh no, metric, I have mistake, because we consider weak convergence only in norm space by functionals. We don't describe the joint of function of dual spaces for metric spaces. So let's change it. It's not correct. X is norm space. We define compact set in metric space, but weak convergence we define only. So what means weakly continuous? If xn weakly converges to xn, then f capital of xn go to fx. And let M is weakly compact set. So it attains maximum and minimum too, but we need maximum. By definition of supremum, what we have? By definition, the proof of this fact. By definition of supremum, the exist sequence lies in M such that fxn goes to supremum. Now, let's define it C for shortness. Yes, C is supremum on weakly compact set. So goes to the C. So we obtain sequence. We obtain sequence. By definition of weakly compact, what we can say, what we can do with this sequence? Exists subsequence x and k, which weakly converge to x, 0, some x 0. But our function f capital is weakly continuous. So f of x and k tends to f of x 0. And simultaneously it tends to the C because it is supreme. So immediately what we obtain? So we have construct an element on which weakly continuous functions attains its maximum on weakly compact set. On weakly compact set. And now we're ready to prove Hilbert-Schmidt theorem. I only formulate it for separable case. It is valid in not separable situation, but it is more difficult and more important case is separable case. So Hilbert-Schmidt theorem. For separable case. So let H is separable Hilbert space and with infinite dimension. Let A is self-adjoint and A is a compact operator in H. It's compact. Then exist EK orthonormal basis in H such that it consists from eigenvectors. It consists of eigenvectors. And additionally, if we numerate lambda k in order then the maximum is a norm. The maximum in absolute value eigenvalue is a norm. And of course, if you know that operator is self-adjoint, we know all about spectrum of this operator. What you can say about from what number set it is? Real, complex? They of course real, yeah? Lambda k of course real. Because operator is self-adjoint. So, and I want to discuss a few minutes this existence. This existence you can use only if you have eigenvalue with multiplicity. Because if you have only simple eigenvalues, simple it is multiplicity 1. It is only one-dimensional space of eigenvectors. You know that for self-adjoint operator, if you have eigenvectors which corresponds to different eigenvalues, they're automatically orthogonal. Automatically. But if you have eigenvalue with multiplicity, it may be that you choose not orthogonal basis in this space of eigenvectors, but there exists orthogonal basis. So existence is only for the multiplicity with eigenvalues with multiplicity. But if eigenvalues are simple, if multiplicity of each eigenvalue is 1, all eigenvectors automatically basis, orthogonal basis, automatically by theorem. So it is second way to obtain basis. if you have compact self-adjoint operator, you immediately have a basis of eigenvectors. You have a powerful instrument to construct a lot of orthogonal bases without any checking. By theorem, it's a basis. But if you have, again, repeat, eigenvalue is a multiplicity, and then you find some eigenvectors that are not orthogonal, but in this space of eigenvectors, you can find orthogonal basis. Then this existence is only for this situation. For another situation, it's automatically orthogonal basis. And normalization is up to our hands. Yes, the normalization, the letter n, is up to now. So let's prove. First, proof. Consider quadratic form of operator and consider supremum on the sphere. On the sphere. We know unit sphere is weakly compact. A is compact operator, so quadratic form is weakly continuous. Then what you can say? They exist. It attains maximum. Exist E1, the norm E1 equals to 1, and AX supremum, A E1 E1 gives us supremum of this quadratic form. And what we know about the property of self-adjoint operator? What is supremum of quadratic form? It is the norm. It is the norm. And by lemma 2, looks lemma 2. Looks on lemma 2. If quadratic form of self-adjoint operator attains its maximum, then it is eigenvector. So we immediately obtain that A E1 equals lambda 1 E1, and the absolute value of lambda 1 is norm. Yes? It's just lemma 2. So, and now lemma 1. Now lemma 1. What you can say about this space, the linear span of E1? It is invariant for A. Yes? For A. So by lemma 1, space H1, which is orthogonal complement to this linear span, is invariant for A. Yes? And you know absolutely all about operator A reduced on linear span of E1. One-dimensional space, and here we have eigenvector. But it is invariant for H1. So we can consider the reduction of our operator on this space H1. What we can say about this operator? Is it self-adjoint? Is it compact? So defined as A1, and it is self-adjoint in H1, and A1 is compact in H1, of course, because it is compact in whole space. So you can repeat it with the same operator. You can consider its quadratic form. What you can say? It is weakly continuous, unit sphere is weakly compact. So the exist vector A2 in H1 such that A1, A2, A2 gives supremum of quadratic form of A1 on all x, which is an H1 half is the unit norm. Yes? The same. So A2 is by lemma 2, yes? Again, lemma 2 says us that it is eigenvector, and then the absolute value moreover, we automatically obtain the numeration we need. Is it clear why it is less or equal? Because it is supremum in all space. And this is supremum on orthogonal complement to one-dimensional. So in space with one-dimensional defect. So by mathematical induction, what we obtain? By mathematical induction, we can construct sequence EK, orthogonal system. We construct it by orthogonality. We take orthogonal complement. And AEK equals lambda K EK and lambda 1 and so on. Yes? Why lambda n tends to the 0? First, let's prove that lambda n tends to the 0. By contradiction. Again, by contradiction. If exists number C positive and subsequence such that lambda nk minus not less than C, if exists such number, then but what we know about the orthogonal system in Hilbert space? Any orthogonal system in Hilbert space. When we begin the theme, different convergences. When we act by functionals, we obtain the Fourier coefficients. Our Fourier coefficients lies in L2. So E and K weakly converge to the 0. Yeah? Then A in K converge to the 0 in norm. It is property of compact operators. Yes? But A and K equals lambda nk norm E and K. This norm equals to 1, this greater than C. Contradiction. Operator compact. Operator compact. So it would weakly converge to the 0. It is not converged to the 0. So it tends to the 0. So let's define the orthogonal complement to all elements. Orthogonal complement to all elements. Different to situation. Different to situation. First situation. H0 equals to 0 space. Then we construct basis. Yes? Then immediately all EK is orthogonal basis. Is it clear? Is orthogonal complement to all elements is 0 space. Then this linear span is whole space H. And second opportunity is that this is not 0. It may be. It may be. But what you can say about the operator A, if we reduce only this space, is it clear that his norm less than norm of any operator n, which equals to lambda n for any n? In an we construct on each step here, yeah? By mathematical induction. But lambda n tends to 0. Lambda n tends to the 0. So what you can say about this operator? What you can say of this operator on this subspace, if it is not trivial? His norm is 0. So what is operator? Is 0. Is 0 operator. What it means? What you can say about subspace H infinity? If operator is 0 at this space, and space is not trivial, it is kernel. It is kernel of operator A. Maybe first or second opportunities. So if we have no kernels, non-trivial kernel, we obtain this situation. If we have non-trivial kernel, we obtain this situation. And this subspace can be finite or infinite. So take basis, orthonormal basis in H infinity, so Fk, k, n, or finite number or infinite number. And then Ek, k from 1 to infinity, with basis in kernel, together gives us what? Ek is orthogonal basis to in the H infinity orthogonal, and Fk is orthogonal basis in H infinity. Together it is basis in whole space. Together it is orthogonal basis in H. And some example on this. L2 Ax equals x1, x22, xnn, and so on. So in this, it is compact self-adjoint operator. We know its basis. We know that A Ek equals 1 over k Ek. What you can say about space H infinity in this situation? Equals 0. It is equals to 0. And second, consider A x1, 0, x3 over 3, 0, x4 over 4, 0. What can you describe H infinity in this situation? If we repeat the proof of the theorem for this operator, we firstly obtain first eigenvector, third eigenvector, fourth, 0, here 5, sorry, 5. So we obtain first, then third, then fifth eigenvector, and we do not obtain supremum on the even eigenvectors. Yes. So H infinity here is a linear span of all eigenvectors, all basis vectors with the even number. Yeah, with the even number.